If you've been through the modern education system, it won't come as a surprise to you when I say that we have a little bit of a complicated relationship with mathematics. It remains one of the most feared subjects in school, and that fear extends all the way through into adulthood. If you interview a random person on the street and you show them a mathematical statement with a bunch of Greek symbols and complex notation, they'll probably get this look of dread on their face as they start to relive their traumatic high school math exam experiences. And if you probe a little more deeply, you'll probably get them to say something along the lines of, "I'm just not a math person," or "I just don't get math," or "math just doesn't work for me," that type of thing. And you'll find that they've often really internalized this idea that there's this invisible line in society that somehow separates people who understand math from people who don't. And I think it's really worrying that we're creating an education system that really just is actually traumatizing our math students, especially in this modern environment that we're in, where science and technology and engineering are so important, and they all rely on a fundamental understanding of mathematics. But what's really interesting is that we don't even have a definitive answer for why math seems to stand out amongst all the other subjects in terms of, producing a really poor education experience and outcomes as well. And that doesn't mean that we don't have a lot of theories about what's going wrong, right? So I've read a lot of what people have written about problems with math education. I've spoken to a lot of people about this and, heard their opinions. And generally people's ideas about what's wrong with math education fall into one of sort of four categories. The first one is the idea that the students are the problem, right? Their attention spans are too short. They spend too much time on YouTube or playing games. They don't do the homework, that type of thing. The second idea kind of places the blame at the foot of the teachers, saying teachers aren't well trained enough, they don't understand mathematics deeply enough to teach it properly. They're failing to take dry, boring curriculum material and make it interesting and engaging for students, or they're sticking too rigidly to lesson plans and not adapting their needs to the individuals in the classroom. The third category is maybe the curriculum's the problem. Maybe the government level of math curriculum design is the problem. Perhaps it's too abstract and not practical enough, or, it's missing key pieces of information, or the grade levels move too fast or too slowly, that type of thing. And the fourth category is a relatively new line of thinking, which is, maybe standardized testing is actually a major problem. Maybe it encourages short-term rote memorization instead of deeper foundational understanding. And maybe the way that exams are run and scored is actually unnecessarily punitive for students who are already struggling and behind. There's definitely truth to all of these things. I don't think any of them are completely right, and I don't think any of them are completely wrong. But I have a kind of contrarian fifth opinion about the problem with math education, and it's that math is just hard to learn. Sounds like a pretty non-useful kind of opinion to have, right? But let me explain. One of the things that math is really well known for is the ability to express complex and powerful ideas with incredibly simple and elegant notation. Indeed, some of the most famous mathematical theories ever, like Einstein's mass energy equivalence of E equals mc squared, it looks very simple. Similarly with the Pythagorean theorem, that relates the length of the sides of a right triangle to each other is a squared plus b squared equals c squared, right? There's not that many symbols in these equations, given how famous and influential they are. And that's the thing. If you speak to someone who understands these a little more deeply, they'll tell you they're a little bit more complex than they appear on the surface. What's actually simple is the way that they're written down. And so I just want to focus for a second on the way that math is written down, right? Math notation. You might not have thought about this before, but math notation isn't something that just appeared out of nature. It was actually created and designed by people to serve a purpose. And so math notation is actually designed with three major things in mind. The first one is that it has to be correct, obviously, right? Math notation is not useful if you could manipulate it and end up with invalid results that don't actually correspond to the real world at all. So it has to be correct, right? Logically correct. The second kind of less obvious thing that you might not have thought about before is that it has to be unambiguous. And what that means is, unlike in English, where two people can kind of read the same sentence and interpret it differently, math is designed specifically so that there should only be a single possible interpretation of a particular statement. You should only be able to get one answer. Two people shouldn't read the same thing and be able to get two different answers from the same mathematical statement. That's very important. And the third thing is that math notation is actually specifically designed to be as compact as possible, to use the fewest number of characters and the fewest number of symbols. And I think that this is actually the root of so many problems in mathematical education, right? I'm not saying that this is a bad thing, right? There's very good reasons math is very compact. It's mainly designed to be written and read by math professionals, and for the majority of math history, it was written down with a pen or a pencil on paper, right? So having it be compact was really important for the efficiency of writing it down or sending letters and that type of thing. So I think that math notation is actually wonderful in serving its purpose with math professionals. I'm not saying that I have a better idea of how to do math notation, but I am saying that I think that being optimized for these three things, being correct, unambiguous, and compact, means that math notation is unintentionally designed to be hard to learn. So just to amend my previous inflammatory statement, I think that one of the biggest problems with math education is math notation specifically is just hard to learn. And to give you some examples, I'm going to start off with what a lot of people kind of see as the foundational mathematical statement. And for a lot of the people watching this is going to be the first math likely that you ever saw written down on paper. And it's 1 + 1 = 2. It's a very simple statement on the surface of things. When we start learning this idea as kids, usually how we'll learn it is with physical metaphors, like, okay, Zoe has 1 orange and Joe has 1 orange, and Zoe gives her orange to Joe, and Joe now has 2 oranges, right? That type of thing. Taking groups of objects, combining them, and then counting the whole group. And when we write it down and we start to see the plus operator here, what we start to feel is that plus is like an action, like a verb. It involves combining things, stuff like that. And as a result, we get this little mental picture that the plus is kind of like this little machine where the 2 ones go in and a 2 sort of pops out. Again, we think of it as like an action that's happening. And then we move on and we learn a few more concepts in maths, and inevitably, pretty soon after, we end up at subtraction, right? And we start to look at things like 2 - 1 = 1. And we teach subtraction with similar kinds of physical metaphors. You know, we'll say, okay, well, I have 2 oranges in my hand and I eat one of them, and now I've only got 1 orange left. Again, you can see we're using verbs, actions. We teach with things like, you know, I ate one of the oranges, or I gave one of the oranges away. I take something out. And as a result, we end up with the same mental picture, right? Subtraction being a thing that happens. The 2 and the 1 go in and the 1 pops out. But we've only just learned the most basic rudimentary rules of arithmetic, and already we start to have exceptions to the rule, right? Because unlike addition, when you're doing subtraction, the order of the things that go into the subtraction machine matters, right? 2 - 1 is not the same as 1 - 2, which is in contrast to addition, where 1 + 2 and 2 + 1 are the same. So here's something that now we have to memorize. Not only that, teachers will often strategically avoid the idea of subtracting a larger quantity from a smaller one, because as soon as you start to introduce negative numbers, all of those physical metaphors of counting that we use stop making any sense at all, right? It becomes very confusing for students when they're like, okay, I understood eating 1 orange when I had 2, but if I only have 1 orange, how can I eat 2 oranges and then have -1 oranges left over, right? It doesn't make any sense in that regard. And on top of that, if you're thinking of subtraction as a thing that happens to 2 things, right? Now we've got this weird case where when we have this like negative number, it's like you have 1 - 2, and now you have just the minus sign just with only one thing, just the -1. And so now you have to think mentally, okay, there's 2 cases with minus. There's minus where you're subtracting something from something else, and there's minus where it's just a minus number on its own. And that's far from the only exception to the rule. They just keep getting worse, right? Because remember how I said the order matters? Well, it turns out, if you really want to, you can actually change the order of the terms and keep the result the same but you end up going from something like 2 minus 1 to something like minus 1 plus 2, right? And if you're not a mathy person, you're probably feeling that sense of dread creeping in again as you're remembering the exams where they tried to trick you with where the minus and the plus signs were. And things get even worse when you start to be introduced to terrible statements like this one, like 1 minus negative 2 equals 3. Somehow the two minus signs like turn into a plus, and then you end up with more than what you started with, even those two minus signs. It's like, this is the type of thing that really cements for kids that math is confusing and nonsensical, and you have to remember exceptions to the rule. And indeed, what ends up happening is you end up with just this like laundry list of stuff to memorize. You have simple rules that apply in only a small number of cases, and then this huge list of exceptions to the rules, right? You would probably be not surprised when I told you that the root of the problem ends up often being the compact notation. So we're going to try a little exercise, and I'm going to let you in on a little secret, right? Which is that plus and minus actually don't exist. Reasonably controversial thing to say, but let me show you. What we're going to do is that we're going to think of numbers as being in one of two groups, positive and negative. We have positive numbers that we think of as something like fire, negative numbers that we think of as something like water. And the main idea is that when a positive number collides with a negative number, it cancels out and turns into steam and disappears. Right? So you have a positive and a negative, they combine together and they become nothing, they disappear. And if we start to think of some basic addition and subtraction equations using this type of idea instead of the number system that we were using before, we can think of something like 5 minus 3 being represented as having 5 positive fires and 3 negative waters, right? And it's actually incredibly obvious and straightforward what's going to happen here, right? Which is that the fires and the waters pair up one by one. So 3 of each of them combine and become steam and disappear. And we're left with just 2 positive fires at the end, right? This concept also extends extremely naturally to negative numbers, because if we're looking at something like 3 minus 5, or we could always also write it as negative 5 plus 3 if we wanted to in standard notation. But when we're thinking about things in terms of just quantities that are positive or negative, we have 3 positive fires, 5 negative waters, and it's obvious again what's going to happen. 3 of each of them are going to pair up, disappear, and we end up with 2 negatives left over. So the answer, of course, is minus 2. And when you do things in this way, it's incredibly natural the way that negative numbers get introduced. They don't appear out of nowhere. The minus sign doesn't just pop into existence. You start to think of things instead of this idea of plus and minus. You just have a single operation, which is just combining a number of things that can have either a positive or a negative quantity. And if you'll humor me for just a minute, I'll just display things in an alternative notation that I'm not suggesting is better than normal notation, but it's just an idea for how to think about these type of things. So if we look at the combine operation, we have on the left-hand side just positive 2 and positive 3. And we always display the fact that they're both positive. You can think of those 2 fires and 3 fires, and we end up with 5 fires, with positive 2 and positive 3 combined to make positive 5. Now, introducing negative numbers into this situation is incredibly straightforward, right? Because the positive sign's always shown, and so the positive sign just becomes a negative sign. So we have positive 3 and negative 2 combining together to make positive 1. Of course, we end up with a positive result because there was more positive things to begin with, so the remainder is going to be positive. When we look at things from this perspective, it's really easy to just swap the order of the terms inside the combine and the answer doesn't change, right? It's not surprising when we rearrange the order of the terms, so there's no exception to the rule to remember if things have to be in a particular order. And of course, it means that introducing a negative result is totally easy and intuitive, right? Because we have more negative waters in the combine than we have positive fires. So of course, the remainder is going to be some negative waters left over. We start to think of things as the difference between two numbers rather than these discrete addition and subtraction operations that take in two things and spit out one thing. And all of this stems from just one information hiding rule. All of this complexity comes from just one rule, which you might have learned is that if the first term, that is the first mathematical unit in an equation on the left-hand side, if it's positive, we don't have to write a plus sign there. If it's negative, we do have to write a minus sign in front of the first term, like minus 5 plus 3, right? But if the first term's positive, like 5 minus 3, we don't have to write plus 5 minus 3. And that's literally just to save space and to save having to write plus at the beginning of lots of different mathematical statements. It's just to compact the notation. So much of the complexity involved in plus and minus stems from the desire to hide this 1 plus symbol. And of course, our foundational statement of 1 plus 1 looks a little bit more ugly, slightly more ugly, if we display it instead as plus 1 on one side and plus 2 on the other. But you'll notice it's very similar to that combine notation that I showed you before. We're just always showing the sign for every quantity and thinking about them as just combining a number of compatible things together rather than the plus being an operation that happens. And so when we look at our terrible statements like 3 minus negative 7 equals 10, again, you can probably guess that what's going on here is actually a lot of information hiding. And I'm not picking on Khan Academy in particular. They're a great mathematical resource, but they have a whole series of videos trying to help kids mostly understand what, subtracting a negative number means. In this case, they're trying to explain minus negative 3. They have this whole thing about the number line, and you go forwards, and then when there's a negative, you turn around, and then there's another negative, you turn around again, and they introduce the concept of opposites, right? And, the videos are good quality, but of course, inevitably, it's confusing. You end up with comments with people saying stuff like, I don't get numbers like minus negative 7. It makes perfect sense that you don't understand this type of thing because what's actually going on is basically not subtraction at all. There is so much information happening here that what is actually going on underneath is not 3 minus negative 7, but 3 minus 1 times negative 7, right? 4 out of the 8 symbols are hidden. Half of the whole of the real thing, of what's actually going on here, you can't see. And there are 3 different information hiding rules all happening together that lead to this result. So the first one is that if you're multiplying 2 things together, if they're numbers, you have to show the multiply sign. But if they're not numbers, you can just get rid of the multiply sign. So I don't have to write 2 times y. I can just write 2y. Or in that case, if I'm multiplying 2 by some parenthesis or some brackets, I can just squidge the 2 in there next to them instead of having to write the multiply sign. So what this means is 3 minus 1 times negative 7, we can just drop the times symbol there because we're not multiplying 2 primitive numbers together. So we end up with 3 minus 1 just squidged in next to the brackets there and negative 7 inside the brackets. The second rule that's applying is that if you're multiplying something by 1 or minus 1, you don't have to write the 1. So if you have 2y, yes, you have to write the 2, but if you just have 1y, you can just write y. And if you have negative 1y, you can just write negative y instead. And as a result, in our equation, we have 3 minus 1 squidged in next to the parenthesis. We can just drop the 1 because we're technically multiplying by minus 1. So we just end up with 3 minus and then negative 7 inside parenthesis. And the last rule that's occurring is if you only have one term inside the parenthesis, they're allowed to be removed, right? So I don't have to write 2 parenthesis y, I could just write 2y. And so we can drop the parenthesis and then we end up with this incredibly confusing statement of 3 minus negative 7 equaling 10. And one of the reasons this is so confusing is because a lot of students, when they see 3 minus negative 7, they've never even done multiplication of negative numbers before. They don't know that this is multiplication, they've not learned those ideas, and so we have to teach them some weird kind of halfway metaphor so that they can understand something too early without actually having a fundamental idea of what's going on. Whereas if we were to display it, for example, in this combine notation, you might notice that it's actually impossible to produce a statement like 3 minus negative 7 because we can't just write a minus sign by itself. The only thing that we can do here is like change the order of the positive 3 and the negative 7, but we can't make something that has this hidden multiplication in it. So the notation in this case can actually provide sort of guardrails for newer math learners to not get themselves into a really confusing situation. Remember how I explained the only time you ever have to actually display the multiply symbol is if you're multiplying two numbers? Well, what ends up happening is that a little while later, they will conveniently tell you, oh yeah, by the way, we actually don't even use the multiply sign. You should use this central dot to represent multiply because the multiply symbol looks too much like the letter X. I know that it feels like I'm complaining about something tiny, changing the multiply symbol into this dot, but remember how I explained that like so much of math from a very early age just ends up being about rote memorization because the rules have all of these exceptions to them? It turns out that the way that you memorize applying things in mathematics is incredibly visual, right? You recognize a certain visual pattern that tells you that you can apply a certain rule and get a certain answer. To give you an example, if I take an incredibly simple mathematical statement, like 3 plus 7 minus 5 equals 5, and I replace all the symbols with random Greek letters, very quickly you will just forget what the original statement was. And not only that, I imagine you would be very unconfident in doing any kind of algebra or combining terms or whatever on a statement like this because it's so hard to remember how to apply things when the symbols are different. This is actually part of a much larger process that leads to students becoming alienated from mathematics. The first step is that we teach students these oversimplified concepts because they're too young and we think they can't understand it properly. So we teach them things that are simple but end up having all of these exceptions because they're not the real rules of what's actually happening underneath. So they have to memorize all these exceptions. Then, slowly over time, they change the notation, they change the conventions, they change the rules slightly. That starts to break your ability to memorize and apply rules correctly. That leads to small accumulated mistakes in exams. That leads to declining exam results over time, which messes with your confidence in mathematics and eventually leads to you just abandoning it altogether and deciding something like, I don't get math. This is an incredibly common situation, and if you're the kind of person who felt as a child you really enjoyed mathematics and you really felt like you had a handle on it, and then somewhere around age maybe 13, 14, math just felt like it just ramped to being impossible suddenly, chances are this type of thing happened to you. My condolences, it happened to me as well. And when I was showing you, the symbols changing, there are so many examples of that. Probably the most egregious example for me personally is the division symbol. This thing needs to be just thrown into the fires of Mount Doom or something. It should not be taught. It should not be learned. In fact, the International Standards Organization actually officially recommends in their mathematics standards documentation, don't use the division symbol, right? It's basically only taught in the Western, like the English-speaking education system. The symbol doesn't even mean the same thing in a lot of non-English-speaking countries, so just don't use it. But even if you don't get taught division, you probably got taught ratios, for example. That's another symbol that you have to learn. Taught to you with this colon symbol in the middle. And the thing is, you often end up getting taught division and fractions and ratios and proportions and other things like that, all with just like subtly different rules or with different types of word problems that you're supposed to solve. The thing is, they're all fundamentally exactly the same. And it's that teaching of this idea that you need to memorize a specific case for a specific symbol, even when the underlying rules are actually much more simple and similar. There's actually one incredibly foundational golden rule that underpins all of this type of stuff. Division, fractions, ratios, proportions, like all of that stuff. And it's incredibly important and easy to understand. And to get to grips with it, I'm going to kind of rewind all the way back to that original mathematical statement, right? Which is 1 plus 1 equals 2. And I'm going to show you a little magic trick. Ready? 3, 2, 1. Ta-da! 2 equals 1 plus 1. There is something weird about this, isn't there? Something weird and off-putting about seeing this formatted as 2 equals 1 plus 1. Chances are, if you find looking at this strange, it's because you have subconsciously picked up on this idea that math is supposed to be formatted in terms of problem equals solution. Right? The problem that you're trying to solve goes on the left, the solution goes on the right, and the equals symbol is, again, like an action, something that's happening. It's like the 1 and the 1 combine, and the equals produces the 2. And so when you see something formatted as like solution equals problem, it feels like reading an English sentence backwards. You know, there's something that just feels off-putting about this kind of thing. And I think it's really important to understand that equals itself is not an action that's occurring. It's actually much more simple than that. What the equal sign is actually saying is that you have these two separate blobs of mathematics. One of them is 2 in this case, and one's 1 plus 1. And the equal symbol is just telling you that these two separate blobs of mathematics actually represent the same value, right? They represent the same thing, even though they're two separate blobs, right? And just for your interest, those blobs are usually referred to as expressions, right? So they're two separate mathematical expressions that represent the same value. It's not solution equals problem. And so in this case, 2 equals 1 plus 1. The number 2 by itself is a completely valid mathematical expression, just as is 1 plus 1. You can actually think of the equal sign as basically a set of scales and saying that these two things are perfectly balanced. And just as a pet peeve for me, it's such a confusing term when we refer to this process of algebraic manipulation as balancing equations. They're already balanced. That's the whole point. The equal sign is telling you that these scales are perfectly balanced with each other. As a result, there are some interesting properties of scales that are perfectly balanced. One of them is that as long as I do exactly the same thing to both sides, it'll stay balanced. If I add a 1 kilogram gold bar to each side of the scales, they're going to stay perfectly balanced. And as a result, there's this particular property when we have an equal sign that we can do whatever we want to either sides of the equation as long as we do the same thing to both sides. So if I take my basic equation of 1 plus 1 equals 2, and I say multiply both sides by 3, I end up with 3 plus 3 equals 6, right? Still a valid statement. We know that 3 plus 3 is 6 because we can count it. I can add 3 to both sides, and I end up with 3 plus 6 equals 9. Again, still correct. And then I can say divide that by 3 again, and I end up with 1 plus 2 equals 3. And the reason that I went down this whole rabbit hole explaining what equals is, you look at the fraction symbol. I'll give you a little hint where I'm going with this. If we rotate the fraction around so that the terms are on the left and the right instead, and I point out that the top and the bottom of a fraction, or in this case the left and right, are both separate expressions, you can probably see where I'm going with this, right? A fraction is actually very, very similar to the equal sign. It's something that separates two separate expressions of mathematics and tells you something about them, but they're obviously not equal, right? Because 3 isn't equal to 4. Instead, what that line in the middle of a fraction is telling you is that there's a certain ratio or proportion between the two sides. And in my opinion, the best way to explain ratios is visually with images, with aspect ratios. I have cut out this tall, thin image of our old mate Einstein from before. It's 2 wide and 4 high, the image. 2 wide and 2 tall. Sounds like Too Fast, Too Furious. And as a result, I'm representing it with a fraction that is 2 over 4. So what we're going to do is we'll take our image of Einstein and we'll multiply both the width and the height by 2. So we go from 2 wide and 4 high to 4 wide and 8 high instead. And you'll see that, our fraction's gone from 2 over 4 to 4 over 8. And you can see that even though the image has gotten bigger, it still looks the same, right? The shape of the image is still the same. It's not distorted. It's just larger than it was before. And a similar kind of thing happens when we divide both sides by 2. We go from 2 over 4 to 1 over 2 instead. And you can see that we've got a tiny image of Einstein here, but it still looks like Einstein. It's still the right shape. It hasn't been distorted. So with equalities, we can add and subtract from both sides as long as we do the same thing to both sides. So what about addition and subtraction with fractions or with ratios? Well, if we take our 2x4 image and we add 3 to both sides, that gives us a width of 5 and a height of 7. And you can see that Einstein's been kind of squashed and much shorter and wider than he was before. So the image has been distorted because the ratio has actually changed. Similar kind of thing happens when you subtract 3 from both sides, or subtract 1.5 in this case from both sides. We end up with an image that's 0.5 wide by 1.5 high, and you can see that it's been stretched out vertically. Einstein's all tall and thin in this case. The image has been distorted because we've changed the ratio. So it turns out that the way that division and ratios and all of those things work is that the line in the middle of a fraction functions very similar to an equal sign. But the only thing that you can do is multiply both sides by the same thing or divide both sides by the same thing. You can't add and subtract or square or take the square root or that type of thing. That's like a foundational, incredibly important rule that underpins everything in division and fractions. And of course, division and fractions are vulnerable to the same type of information hiding and compact notation issues that we had previously. If we look at something like multiplying 6 by 5 over 3, you might remember from doing fractions that if you multiply a number by a fraction, you multiply the number into the top part of the fraction into the numerator. So 6 by 5 is 30. This is like a confusing edge case that occurs as a result of us hiding the fact that there's a secret over 1 actually happening here, because the rule is you can hide denominators if they're 1. You can hide the bottom part of a fraction if it's 1, because anything divided by 1 is just itself. And in this case, if you understand that the bottom half of the fraction is hidden, you'll understand there's only one rule, right? Which is that you multiply two fractions together and you multiply the top by the top and the bottom by the bottom. So 6 by 5 is 30 and 1 by 3 is 3. It's extremely straightforward. Again, more exceptions to the rule because of the information that's hidden. But I think the most egregious and confusing example of information hiding that happens in fractions is this particular rule, which is you are allowed to merge fractions that have the same denominator. So in this case, we have 3 over 7 plus x over 7, and we're allowed to rewrite that as 3 plus x over 7. Essentially, we're just avoiding having to write the denominator twice. We're avoiding having to write that second 7, and we're saving time for writing math down with a pen in the 18th century, you know? But what ends up happening as a result of this is that it creates situations where the answer is extremely obvious and easy and straightforward, but it becomes very confusing because it's displayed in a way that doesn't make the answer obvious. So if I took a fraction like this, x plus 1 over x, and I asked you to solve it or simplify it or cancel the terms or something along those lines, don't worry if you have no idea and you can't remember fractions at all. You know, if you try to do this, you'll probably sort of get stuck down a hole thinking about like how to cancel with the plus there, and you might end up with something like 1 as the answer because, you know, you canceled both the x's and the 1 was left over. And if I told you that the answer that I'm looking for is actually 1 plus 1 over x, you'd probably look at that and you're doing the confused math lady face and trying to figure out how that answer results from the thing on the left. The confusion here is entirely due to the information hiding caused by that rule that I just showed you, because if we look at something like x plus 1 over x, it's the reverse of the rule that I showed you before. This is the result, right? So x plus 1 over x is actually the simplified version of x over x plus 1 over x, right? Because as I mentioned, we don't want to have to write the denominator twice. This is the same as that case that I showed you before. So we take x over x and 1 over x and we compress them into x plus 1 over x. But if I was to write this originally, like I showed you, as x over x plus 1 over x, it's incredibly simple and straightforward what you can do here, right? Because one of the first things that you ever learn about division when you're like 7 years old is that if you divide something by itself, you get 1, right? 7 divided by 7 is 1, 20 divided by 20 is 1, and so x divided by x is 1. And that's your answer. That's the thing I showed you before, 1 plus 1 over x. The only thing that I applied was the the most rudimentary idea in division. That's all. I didn't do any fancy fraction stuff. But if you look at like these rules, for example, they're written down here. It's a fantastic website, algebrarules.com, that lists simplified cases for a lot of different algebraic tricks. So many of these tricks are actually redundant and caused by the different or compact ways that we can show the notation. The notation's causing us so many problems here in terms of making it not obvious what's actually going on. But if we're talking about things in math that are confusing and require a lot of memorization, there's nothing more extreme than the absolute mother lode, which is something called the order of operations, right? The order of operations. To me, it sounds like a 15th century secret religious cult or something like that. Chances are you learned it as a heinous acronym like PEMDAS or BODMAS or DADBOD or something like that. And PEMDAS, for example, stands for parentheses, exponents, division, multiplication, addition, subtraction. And it tells you that when you see a viral social media post like this, how you're supposed to resolve this and get an answer. This kind of thing goes viral on social media every couple months, and there's thousands of comments of people arguing whether the answer is 1 or 9, or some people get 25 or 0. So it's obvious that people aren't retaining this information about the order of operations well, right? But this is actually a classic example of, you remember why I told you we should just get rid of the division symbol? Yeah, the reason that you can actually get 1 or 9 in a problem like this is because the order of resolving the division symbol specifically is ambiguous depending on whether you learned PEMDAS as in multiplication division or PEDMAS as division multiplication, right? So yeah, we need to get rid of that symbol. But the problem still remains that the acronyms are not easy to remember. They're very easy to make small trivial mistakes, and they're generally penalized quite harshly in maths exams. And so again, I'm going to let you in on a little secret. I have an alternative order of operations, which is the perfect acronym, incredibly easy to remember. You'll never forget this one. It's really easy to apply as well. I know I'm talking it up. The new order of operations that you should try is just the letter P. Not PEMDAS, just parenthesis. That's it. Parenthesis or brackets, if you want to refer to it as that. And what it means is like you just put parentheses around everything until the order that you're supposed to resolve things in is just completely explicit. There's no other way to resolve it other than specifically the way that you've written it down. You don't have to worry about the order of division and multiplication or addition and subtraction, that type of thing. So you can actually see visually in this case that there are two different ways that I can group the terms here to produce two different answers, right? Up the top, we do the multiplication inside, so first, and we end up with 1 as the answer. And at the bottom, we do the division first on the inside, and we get 9 instead as the answer. So that's the kind of way that people produce two different answers to that viral math problem. But again, if you'll humor me, if we look at this in a slightly different notation, because, you know, this is kind of overwhelming the number of parentheses or brackets that you can see here. If we display this with a little bit of shape and color, really quite obvious the order in which we're supposed to resolve things, right? In this case, we can't resolve the multiply in the middle because there's a combine there that we have to do first. We can't resolve the divide because there's a multiply we have to do first. But the inner combine, it just has two numbers in it, so we can just add those two together. We get 3 as a result. Because we only have one thing in the combine now, we can kind of just get rid of it, and we end up with this multiply, which is 2 by 3 in the middle. We can multiply those numbers and we'll get 6. Again, we've now resolved the multiply, so we can get rid of it. And we end up with just a divide at the end, and 6 divided by 6, obviously 1, and so 1 is our answer. And if I format both of those groupings that I showed you in this different notation, right, it's incredibly straightforward and obvious the order in which you're supposed to do things and what you're supposed to do. I would be reasonably confident that most people being shown this notation for the first time, not explained at all how it's supposed to work, would be able to get the right answer. And I know that it looks childish and overbearing, and, you know, obviously you couldn't draw these out by hand, but it's just food for thought in terms of maybe alternative systems that we can use early on to teach people in the education system to give them a more intuitive understanding and feel like they're a little bit more in control, that they understand what's going on. And I could not find a better explanation for how confusing these concepts are, then again, I'm sorry for picking on Khan Academy. There's a Khan Academy video, well, a whole series of videos actually explaining the order of operations. And of course, the comments are full of stuff like this. I don't get it. Can someone explain? And I didn't make this up. I swear. The first response to this comment, the first reply is this. It's like 4 paragraphs of text. And it has votes up, you know? And I think this is kind of the perfect analogy for mathematical notation in general, because a question like this, getting an answer like that, is so similar to the way that math notation itself is like a zip file. It's like this compressed version of the actual math, and you have to uncompress it inside your brain correctly to be able to even start solving the thing to get the right answer. And if students don't realize that that's happening, or if they're not good at it, they end up making mistakes with things that are actually nothing to do with mathematics. It's just due to knowing the rules of how the notation is able to be compacted and leave things out. And I think it's so important to understand that mathematics itself is an amazing, wonderful thing. You would not have to try hard to convince me that there's something divine about mathematics. You know, it's like looking behind the curtain and being able to see into the mind's eye of the universe. Really. But I think the problem is that people tend to give the same level of reverence and respect to mathematical notation. Right? They have this idea that math notation was like handed down on a stone tablet from God or something like this. It's like, could not be further from the truth, right? Mathematical notation is just a bunch of accumulated estimates and mistakes and curiosities that were contributed by thousands of people over literally hundreds or thousands of years while they were still learning how math even worked in the first place. And the reason that we use the notation that we have now is because everybody uses it and we're stuck with it, right? And I'm not saying that I could easily come up with a better idea for modern mathematical notation for professionals. It's fantastic for what it's used for, right? I just think that it's really important for us to acknowledge that it's not easy to learn, and it's not designed to be easy to learn. Right? So if I can leave you with one particular idea from watching this video, it's that if you see a bunch of Greek symbols and complex notation like this, you're not dumb because you don't understand it. You don't understand it because it's hard to understand.